The three DC voltages for the bias transistor in the diagram below are the emitter voltage VE, the collector voltage VC, and the base voltage VB. These voltages are with respect to ground. The collector voltage is equal to the DC supply voltage VCC less the drop across RC. So the mathematical relationship for determining the collector voltage is VCC minus the collector current times the resistor current. The base voltage is equal to the emitter voltage plus the base emitter junction barrier potential, VBE, which is about 7/10 of a volt for a silicon transistor, just like we saw for the diode. So the base voltage, VB, is equal to the emitter voltage, VE, plus VBE. In the configuration of the figure below, 17.5, the emitter is the common grounded terminal. So VE is equal to 0 and VB is equal to the barrier voltage, or 7/10 of a volt. The two DC bias sources can be replaced by a single DC source and a resistive voltage divider. Although there are other bias methods, this one is the most widely used. The voltage divider bias configuration uses a single DC source to provide forward reverse bias to the resistor, as shown in the diagram to the right. Resistors R1 and R2 form a voltage divider that provides the base bias voltage. The resistor RE allows the emitter to rise above the ground potential. The voltage divider bias provides a very small base current to the resistor compared to the bias current. For a properly designed circuit, the loading effect is negligible and can be ignored. The input resistance then at the transistor base depends upon beta DC and is approximately Rn equal to beta DC times Re. For the base voltage, using again the voltage divider formula, which you should be very familiar with, this R2 over the sum, R1, R2, you get the following equation of the approximate base voltage for the circuit 17.6. Once you have determined the base voltage, you can determine the emitter voltage, VE, for a Pnpn transistor. So VB is equal to approximately R2 over R1 plus R2 VCC, and VE is equal to VB minus the barrier voltage, or 7/10 of a volt. So again, you need to keep track of these relationships, write them down in your notebook, put a brief explanation of what they're all about. So in this example, they want us to determine then those values: VB, VE, VC, VCE, IB, IE, and the collector current IC. This is a 2N3904, which is a general purpose transistor with a typical BDC of 200. So we can see the diagram here. We've got a 22k ohm resistor on the base, a 10k ohm resistor on the base, which forms a voltage divider. We have VCC set at 30 volts. We have the collector resistor, 1k ohm. We've got a beta DC of 200, and we've got a emitter load resistor of 1k ohm. So the base voltage then is approximately, by the relationship, VBE is equal to, or approximately equal to, R2 by R1 plus R2 VCC, which gives us 9.38 volts. So therefore, VBE is equal to VB VE is equal to VB minus the barrier voltage, 7/10 of a volt, which gives us 8.68 volts. Now that we know VE, the voltage across the emitter, you can find the emitter current by Ohm's law. So VE by RE gives us 8.68 milliamps. Since alpha DC is so close to 1 for most transistors, remember that's our 0.995 relationship, it is a good approximation to assume that the collector current is equal to or approximately equal to the emitter current. So IC, the collector current, is equal to 8.68 milliamps. So if we use the collector current, IC is equal to beta DC by the base current, and solve for the base current, we have IB is equal to IC by beta DC, or 43.4 microamps. Since you know the current then for the collector, you can now find the voltage drop, VC. So VC is equal to VCC minus the collector current, the resistor current is equal to 30 volts minus 8.68 milliamps times 1 k ohm gives us 21.3 volts. Since V, collector to emitter, is the collector to emitter voltage, it is the difference of VC and VE. So VC is equal to VC minus VE, or 12.6 volts.